Okay, dear friends, now our next paper under consideration is uh, 0625 paper 4 variant 3 and October November 2024. Okay, and let's start from question 1, which says state the difference between a scalar quantity and a vector quantity. So it's not that much big deal, very simple. It's not that much big deal, very simple answer. So scalar has only magnitude, vector has both magnitude as well as direction. So they want a difference, so I can say vector as direction while scalar as no direction. Define momentum, it was in the previous question also. So it is the product of mass and velocity. Momentum is denoted by capital letter P, and P is equal to m times v, means product of mass and velocity. A test car crashes into a barrier to test the safety features. The test car has a total mass of 950 kilograms. So mass of the car is given. It is moving with constant velocity from time t is equal to 0 for 4 seconds. So it took 4 seconds time. At t is equal to 4 seconds, the car hits the barrier. Figure shows the car as it hits the barrier. During the test crash, the resultant force acting on the car is this. So that is the resultant force. The car takes 1.5 seconds to come to the rest. Time is given, takes to come to the rest. So final velocity is given, that is 0. The deceleration is uniform. Calculate the initial velocity of the car. No problem. Why no problem? Because we have force, we have time, we have final speed, we have mass of the car also. So the second law of motion, resultant force F is equal to ma. Then F, it is equal to, okay, still let it be F equal to m. A is equal to v minus u over t. Now we will make u as the subject of equation. U as the subject of equation. So let's arrange the equation. So see, my dear friend, it will become F times t is equal to m into v minus u. Then we can say F times t over m is equal to v minus u. Now force is given, that is 27,000 times t, which is 1.5 over mass, which is 950 kilograms. It is mentioned there. V is equal to 0 minus u, and we will be just using it negative, but remember it is always, because there is a change in momentum, mv minus mu, please. There is a change in momentum, mv minus mu, and remember change in momentum is always kept positive. So anyhow, we can say u is equal to, now let us check the answer, 27,000 times 1.5 equal to this divided by 950. Answer is 42.6. So we can round it off to 43 meters per second. Don't worry about the negative sign and don't need to write it. Always remember that whenever we are calculating the change in momentum, we are calculating change in momentum. Change in momentum is always positive. Okay. So let's move forward now for the next part. On figure 1.2, sketch the speed time graph to show the motion of the car from time t is equal to 0 until the car becomes stationary. Until the car becomes stationary. So what should we do? What should we do? 2 marks are there. Let's go back. No clue is there in our mind here. See, this is so important work. The deceleration is uniform. So it should be a straight line. Deceleration, so it means we can make it like this. But problem is the car comes to rest. So here car is not coming to rest, car is still having some velocity. That will not be considered correct. That will not be considered correct. What do you think? Is it okay or I should bring it to 0? Let's read it again. Constant velocity from t is equal to 0 for 4 seconds. At t is equal to 4 seconds, the car hits the barrier. During the test crash, the resultant force acting and the car takes 1.5 seconds to come to rest. So up to 4 seconds, no need, it's okay. We should not touch it to 0. It will be up to here. So that's fine. So on figure 1, and why I have drawn a straight line with negative gradient? The reason is it is decelerating, but decelerating uniformly. If the line will be curved, then the uniform deceleration is not there. It is curved. It is non-uniform deceleration. So deceleration is uniform. Okay. So let's move forward now for the next
But
question.
should it start at 0?
No, velocity is not 0.
But
You
they
think?
said like motion of the car from time 0 till the car becomes stationary. So should it start like from 0, then hits 4 seconds?
Then again 0. No. Okay. Yes, others comment. Emma, your comment. Muhammad Tariq, completely silent. Please comment on this. Yes, my dear. Is it correct?
Yeah.
Wait a minute. Now, what I'm thinking, Mariam, I was expecting you people. So, see, first of all, it is moving with constant velocity from t is equal to 0 to t is equal to 4 seconds. At 4 seconds the car hits the barrier, and then it takes further 1.25 seconds to come to rest. So it means I have whatever, and then when it comes to rest, or it is decelerating, so it's decelerating uniformly. So whatever I have done, see, they said the graph shows the motion of the car from t is equal to 0 until the car becomes stationary. So this is not correct. It should be something first going horizontal, because first 4 seconds the speed is constant. Here from 0 to 4 seconds speed should be constant. The car becomes stationary. See, 4 seconds. So see, this is 2, 4, this is 6. It takes 1.5 seconds. So now see, less than 2, something like this. This will be the correct graph, dear friends. I was expecting you to something like this. See, why did I do this? This is 4, of course this is 2, so this is 6. So further 1.5 seconds it took to come to rest. So it means close to 6 seconds. 4 plus 1.5, 5.5. So in this way it's okay. So now the graph is the correct graph for this question. Please, if you have any doubt, now ask me. See, first 4 seconds very clearly mentioned where I circled. It moves with constant velocity, and it's a velocity time graph. If it is moving with constant velocity, so graph should be a straight line in constant velocity, horizontal line. And then it takes 1.5 seconds to come to rest, and when it is coming to rest it keep on decelerating but uniformly. So graph will be again straight line, and in almost 1.5 seconds its velocity will become 0. That's what I have shared here with you people. In first 4 seconds constant velocity, and then in the last 1.5 seconds, 1.5 second, it will decelerate and come to rest within 1.5 seconds further. So it means up to 1.5 seconds, 5.5 seconds, because 4 seconds plus 1.5 seconds total will be 5.5 seconds. See here 4, and roughly I have made it is 6 seconds here. So it will be before 6 seconds, something like this. Now it is perfectly according to the given data or the information in the question. But no need to mark here by the 6 seconds, because it is not there in the question. It was just for explanation purpose. Describe an experiment to determine the spring constant of a spring. State the apparatus you need. Details of how to take measurements, how to calculate the spring constant. You may use the space below to draw a diagram. Label a diagram as part of your answer. As part of your answer, this is Hooke's law. Basically, how many marks are there? 4 marks. No need to draw the diagram. You can say and the spring from a support on tripod stand on a stand, measure the initial length using a ruler meter rule, you can say. Then what to do? Attach a weight, or load, weight from the lower end of the spring and measure new length of the spring. Just hope slow on. I'm trying to. And now calculate the extension. Now calculate the extension, weight or force, you know. Then, my dear, calculate the extension by subtracting initial or original length. Subtracting initial length from the final length or stretched length. Final length. In this way, you will calculate the extension, and now K is equal to what? F over X. I think this is more than enough for 4 marks. And one precaution, if you want to take the game, that write one thing more, that always do this thing, that repeat the experiment with different values of weight, because in this case weight is independent variable that you are changing. Please, my dear friends, if you have any question, any query, any doubt here, please feel free. Now let's move forward. Next question is, figure 2.1 shows a baby in a baby bouncer. The baby bouncer consists of a holder suspended from a spring. The baby pushes his feet on the ground and bounces gently up and down. So now two springs Q and R are tested to determine their spring constants. Each spring is tested up to its limit of proportionality. Define the limit of proportionality. It is the maximum weight that can be applied till force over extension is equal to constant. Load to extension is constant, in other words K is constant. And if we have to write it in terms of graph, then my dear friend, graph will be as long as the graph is a straight line, so that is the limit of proportion. And when it starts to bend, the limit of proportionality is exceeded. So it is the maximum weight that can be applied till f over x is constant. Mean after the limit of proportionality f over x, which is equal to k, it will be no more constant, it will start changing. The numerical value of it will start what? Changing. Now, table shows the results of the tests. Spring Q. Spring constant is 7.8 Newton. R, not Newton, 7.8 Newton per centimeter. R, 1.1 Newton per centimeter. The total weight of the baby and the holder is 120 Newton. Calculate the extension of each spring for this weight. Extension of each spring for this weight. Very simple. For K, I am writing XQ, that will be equal to KF over K, because you know F is equal to KX. So XQ is equal to F over K. F is how much? 120. K is how much for Q? That is 7.8. So when we will simplify 120 divided by 7.8, answer will be 15.38. So I can write 15.4 and it will be in centimeters. Similarly, for XR, that will be again F over K, that is 120 over 1.1. 120 divided by 1.1, 109. So that is 109. So we can write here 109 centimeters. So greater extension will be there when the spring constant is what? Smaller. So, my dear friends, after this, let's see what is the next question. Next is, the unstretched length of each spring is 25 centimeters. Unstretched length of each spring is how much? 25 centimeter. Again, the stretched length of each spring is 25 centimeter. State and explain which spring would be more suitable for the baby to bouncer, for the baby bouncer in figure 2.1 spring. Wait a minute. See, this is maximum 100 centimeter and already this is so 140. Of course not R, because R is already producing how much? 109 centimeters. So Q, because it produces suitable, you can say, extension into this one. So spring Q is the correct answer. R produces too much. Q explanation you can give. Because, let me write, spring R produces too much extension. Too much extension with low value of K. So like this, RQ is suitable because it produces correct length or suitable extension such that baby can touch the ground with feet or just reach the ground with feet and then bounce back. Okay, my dear friends, so let's move forward now. So this was about extension and this. So this is up to this moment general physics topic is covered for this paper. And stay blessed, my dear friends.